Welcome back to the sixth session of Electrostatics. Friends, in the last class we understood the concept of electric field, the definition of electric field, the equation of electric field and the SI unit of electric field. As we know that the electric field is a space property, then how to represent the electric field? For this question, the answer was developed by Michael Faraday in a non-mathematical way to visualize the electric field. He used a non-mathematical way called as electric field lines to represent the electric field. Then, what is meant by electric field lines? It is also called as electric lines of force. Electric lines of force or electric field line, it is a path in an electric field, straight or curved, such that the tangent to it at any point gives the direction of the electric field at that point. Here, the electric field line, it may be a straight line or a curved one. If it is a straight line, the straight line itself indicates the direction of the electric field. But if it is curved, then draw the tangent to the curve. Already we know that tangent means the line which touches only one point of the arc. So that is, draw the tangent and direction of the tangent will give the direction of the electric field. So that is why electric field line is a path in an electric field, straight or curved, such that the tangent to at any point gives the direction of the electric field at that point. Then, after studying the definition of electric field lines or electric lines of force, let us understand some important properties of electric field lines. Henceforth, I am using EFL rather than electric lines of force or electric field lines. First property says that the electric field lines start from positive charges and end on negative charges. If there is a single charge, they may start or end at infinity. Then what is the meaning of this? Already yesterday we said that how the electric field will be produced by a positive charge as well as a negative charge. If a source charge is a positive charge, the electric field line or the electric field is radially outward. Radially outward means it starts at the core of the positive charge and it spreads till infinity. It ends at infinity. Or if the negative source charge is there, the electric field line starts from infinity and ends at the core of the negative charge. The same concept. Rather than using the word electric field, we are using electric field lines. If there is only one charge or positive charge is there, electric field line starts from the positive charge and at infinity. Or if there is only negative charge, they start at infinity and end at the positive charge, negative charge. Or if only one charge is there, they may start or end at infinity. I will explain about this afterwards. In a charge-free region, electric field lines are continuous curves without any breaks. Please keep it in the mind, it is completely unbreakable or continuous phenomenon. So that is why we used here the word called continuous curves without any breaks. Electric field lines are continuous curves without any breaks. The next one, the definition itself is written as a property of the electric field lines. Tangent drawn to the electric field line at any point gives the direction of the electric field. That means what? If we draw tangent to a curve, then the direction of the electric field will be identified by the direction of the help of the tangent. The next point is two electric field lines can never cross each other. A very, very important property. What is the meaning of this? Suppose if there are two electric field lines, say 1 and 2, if both are intersecting like this, if they are crossing each other at this point, then if I draw a tangent, if I one draw, this is the direction of the electric field due to this line, and if I draw the tangent to this one, this is the direction of the electric field at that point. Look at this, only one point having two different directions at one point. So this is highly impossible. That is why two electric field lines never cross each other. This is the main important property. The next property of the electric field line is electric field lines do not form any closed loops. Loops means the starting point and the ending point should be same. For example, if you take a circle or a bangle, the end point and the beginning point both are same. It completes one cycle. That is called as loop. So, but electric field lines do not make any closed loop. Next property is electric field lines are always normal to the surface of the conductor, both while starting from or ending on the conductor. So look at this. They said here they are always normal. Normal means perpendicular. The electric field lines are always normal to the direction of the electric field with respect to the conductor. And the last point is very important point is equidistant electric field lines represent uniform electric field, and the non-equidistant electric field lines indicate non-uniform electric field. So what is the meaning of this? So let me draw some electric field lines like this. So suppose if I draw the electric field lines like this, so this is the direction of the electric field. Look at this. All three lines are equidistant, hence this is referred as a uniform electric field. This can be referred as uniform electric field. Suppose if they are at non-equidistance, let us say like this. One is like this, another one is like this. So this is also electric field only. So this is the direction of the electric field. But look at this. These all three lines are non-equidistant, hence this is called as non-uniform electric field. So these are some important properties of electric lines of force. Friends, in the examination for 2 marks or the 3 marks, that is question number 11 or question number 19 will be asked on this topic. So that is, mention any two properties of electric field lines. You can write any 2 out of 7, or else mention the properties of electric field lines for 3 marks, that is question number 19. So you can write any 3 out of 7. So these are some important topics of electric lines of force. Suppose if this question is not asked about on the topic electric lines of force or EFL, they will ask another question that is very important topic, that is, draw the nature of electric field. Draw the nature of electric field when they will give some cases, that is, if source charge is positive, if source charge is negative, if the product is less than 0, if the product is greater than 0. In such cases, we need to draw what is the nature of electric field. So in such cases, let me take those 4 important cases. This is also asked in the examination for 2 marks. So now, special cases about EFL. There will be some important electric field lines. So let me take case number 1. Cases. So in that, number 1, first case says that if source charge is positive, that means Q is greater than 0. If Q is greater than 0, obviously we will know that source charge is positive. So in the examination, draw the electric lines of force or sketch the electric lines of force if Q is greater than 0 or plus Q. Very simple diagram. As I said in the property number 1, if the source charge is positive, electric lines of force will start from the positive charge and at negative charge. So just draw the lines. And the direction plays very important. So now this indicates if source charge is positive, electric lines of force are radially outward. So this is the lines of force if source charge is positive. Suppose if source charges are negative, so case 2 says if source charge is negative, Q is less than 0, that is for minus q. For minus q, so now we can draw the lines of force like this. Since it is a given charge, it is negative charge, put a negative sign at the center. As I said, now this is now. So here you'll understand the property, first property of the electric field lines. Look at this. If the source charge is positive, they start their journey from the core of the positive charge. Where they are going to end? They are not going to end at all. So now if there are two charges, say positive charge and negative charge, these charges start their journey and end at this negative charge. Suppose if there is only one charge, say case 1, if there is only one charge, so they will start their journey continuously the curve, extend radially outward, and hence they end at infinity. They will end at infinity here like this. They end at infinity. Similarly, if source charge is negative, they start their journey from infinity and they are moving towards the core of the positive charge. They end at a negative charge. And the case 3 says, if both are, if Q1, Q2, if Q1, Q2 or say Q1, Q2 greater than 0. Greater than 0 means, here they say like charges. Look at this. Both are the product of the both charges will be more than 0, that is positive. Hence we can say that like charges. You can see just be right here. These are of like charges. Like charges. If they are like charges, what is the nature of electric force between them? Time being, I will take only both positive charges. You can take negative also. So now if I take this positive charge, this is positive charge. One more positive charge here. One more positive charge here. Then one electric lines of force goes like this. Another electric force lines goes like this. Suppose if one charge starts journey from this side, it will go, since it is experiencing, we know that the property of electric charges, they repel each other, like charges repel each other, it bend like this. Similarly it comes, bend like this. So it goes, bend like this. So bend like this. So this bending phenomenon of the electric charges takes place. So put the arrow mark. Arrow mark plays very important role. Look at this. With this we can decide, we can know that, we come to know that this region is there, no? This region is high repulsion region. It is very high repulsion zone. That is why we can say that if the product of two charges is more than 0 or greater than 0, or if the both charges are like charges, they repel each other. So with the help of this diagram, we come to know that they are repelling each other. Hence it is going like this, going like this. This zone is there, no? High repulsive zone it is. So that it's like charges repel each other. So we can represent the electric lines of force diagrammatically using the case 3. Then if you go for case 4, so if you go for case 4, case 4 says that, so now if it is less than 0, Q1, Q2 less than 0. If a Q1, Q2 less than 0 means, obviously you will come to know that it is what? Unlike charges. Unlike charges means what? They attract each other. Unlike charges, they attract each other. If the unlike charges attract each other, so we can draw the electric lines of force. So it is very important. One is positive, another one is negative. First is, since they are, as I said, if the source charges are positive and negative, electric lines of force start from positive and end on negative. So draw a straight line. So this is one point. Similarly, one more charge line go like this. It goes like this. All the electric fields starting from positive charge and ending on negative charge like this. And if you go right, then it will go on. Electric lines of force will come like this. Again, put the arrow mark. As I said, arrow mark plays very important role. So put the arrow mark, always going from positive to negative. Positive to negative. Look at this. This is the nature. this region is there, no? This region is highly attractive region it is. So it is, you can call it as attraction region or attractive region it is. This is attractive region, here is the repulsive region. Friends, in the examination for 2 or 3 marks they will ask a question asking that sketch electric lines of force if Q is greater than 0 or if Q is less than 0 or Q1, Q2 greater than 0 or in case of like charges or Q1, Q2 less than 0 or in case of unlike charges. If they ask in the examination, so based on the special case, based on the property, you can draw the electric lines of force. Afterwards, after studying this, if I allow these electric lines of force pass through a limited area, then we can call it as with a new term called as electric flux. One more very important concept of the topic electrostatics. Here I am considering a uniform electric field. Suppose if I allow these electric lines of force pass through a certain area, how exactly it behaves, that will be our next concept called as electric flux. Electric flux denoted by small letter phi subscript e, phi e, electric flux. What exactly it says? It says, so let me explain diagrammatically. Suppose if I consider n number of lines of force like this, 1, so this is the direction of the electric field. This is uniform electric field. In this electric field, suppose if I keep a surface area, and suppose if I keep a surface area with a normal n, so then what exactly happening to it? So let me draw the surface area. Suppose if I draw a surface area of area delta S with a normal say n cap, look at this. This is the direction of the electric field. Here, the electric field and the normal of the surface of area delta S, or you can say A, both are parallel to each other. Hence, maximum number of field lines are passing through that particular area. Suppose if I tilt the area by say, any angle, let me draw one more electric lines of force. So this is the electric lines of force. Suppose if I draw the surface area other than that an angle, so now the normal changes direction like this. This is now n cap. This is the direction of the electric field. Look at this. Then the normal of the surface area subtending an angle theta with respect to the, suppose if I draw one more electric field lines here, so you can notice very properly. So now, so this is indicating the direction of the surface area. And afterwards, if I continue, look at the diagram now. Here, only limited number of area lines are passing through this area. That means what? The electric lines of force are passing through a certain area based on the direction of the surface area. Suppose if I multiply this electric field to this area, that is electric field and surface area delta S, then look at this. When the angle between the electric field and the normal of the surface are parallel, maximum number of lines are passing. Suppose if electric field lines are less, that means what? If substance other than 180 degree, other than say unparalleled. So in case of unparalleled line, so now look at this. Only few lines are passing through this. So that means what? It's purely depending on the direction of the surface area, that is theta. So let me take a dot product. E delta S. if electric field and the area vector both are parallel, then we can have maximum lines of force. So we have maximum flux density. So if the direction of the area quantity changes, then or it subtends an angle theta with respect to the direction of the electric field, the lines of force through that particular area changes. So that we can say that there is a relation between the area vector as well as the electric field that can be written as E into delta S. But if the electric field and the area vector are parallel to each other, we have maximum lines of force. If the area changes, that means if the direction of the area vector changes, then lines of force decreases. That means both are parallel, more number of lines. If not parallel, then lines of force decreases. That means it's purely depending on the dot product. That is, you can write here E dot delta S will give you the electric flux. Phi E is equal to E delta S. Then if I extend this one, I'll get it. As we know that it's a dot product. So dot product, if I open, then I'll get a cos theta. Here cos theta is the angle between vector E and the area vector delta S. So now mathematically we express the meaning of electric flux. Then what is the definition of electric flux? So now definition says here electric field lines are there, they are passing through the particular area. So that means what? Number of field lines passing through the area. So area delta S. Here is delta S is there. So in some book they have taken even A also. So this expression can be written as E A cos theta. It is also holds good. Delta S means small area. So we have small electric flux. So total area phi E is equal to A cos theta. Then if I write the SI unit of electric flux, SI unit and dimensional formula. So in one time it is asked, write the SI unit of electric flux. The SI unit of electric flux is Newton per coulomb meter square. Very, very important. Newton per coulomb meter square, and dimensional formula is m L raised to 3 a raised to t raised to minus 3 a raised to minus 1. So now these are the some points regarding the electric flux. Thank you.